We are live, so hello again, the second talk today. Hello, Kevin.
Hello.
And pushing C# to new places with NativeAOT, that's super interesting. So I will not take your time. Have a nice talk, and we are all listening.
All right, so let's get started. So thanks for the introduction. My name is Kevin. I'm a software engineer at Datadog. And today I would like to talk to you about pushing C# to new places with NativeAOT. So let's start by defining what is NativeAOT. Basically, I assume that you already know that .NET assemblies are compiled to IL, and then the first time you're going to invoke a method, the JIT compiler is going to kick in and convert the IL to native code. This has a cost, and so this is going to increase the loading time of your application. And so to get around that, there are tools available, Engine for .NET Framework and Ready to Run for .NET Core, that allow you to perform this step at compilation time. And NativeAOT that is going to ship with .NET 7 goes one step further and compiles your application as a single standalone native application or library. And so the difference between NativeAOT and Ready to Run is not easy to understand. And so the idea is that Ready to Run is going to produce a .NET assemblies with, in addition, some functions compiled ahead of time. So if you look inside of it, you will have everything that you have in a classic .NET assembly, so the IL, and aside the native code. And in an actual application, it's going to behave exactly like a .NET assembly. So you can dynamically load other .NET assembly, you can emit code at runtime, and so on, everything you could do with a normal .NET application. On the other hand, with NativeAOT, you are going to produce a native library or application. And because it's purely native, it will not contain any IL, and as a matter of fact, the JIT compiler will not be included. And because of that, you have all the same limitations as a native application. And so, for instance, you cannot load a .NET assembly at runtime. You can reference one at compilation, but at runtime, you can't do all the things that you could do in .NET. And likewise, you cannot emit dynamic code. And so why would you want that? Well, the idea that you will get a faster startup time, though I'm not sure that it's going to be actually faster than Ready to Run. You are going to get a lower memory usage. And here by memory, I mean both disk space and RAM. That's because since you don't have the IL and you don't have the JIT compiler and the framework is trimmed, the binary is going to be much smaller. And last but not least, you will get better native interoperability, which is the subject of this talk. And just to make it clear, this is not really a talk about NativeAOT, but rather about native interoperability. And so thanks to NativeAOT, we can write extensions for native applications, for some native applications for which we couldn't use .NET. And so I will show a few scenarios where we're going to write extension for those applications, and I will explain the mechanism happening under the hood. And so to get started with the first scenario, can we use .NET to write a .NET profiler? So if we have a look at the .NET Profiler API, we need to export a getClassObject function that is expected to return an instance of iClassFactory. iClassFactory is going to return an instance of iCoreProfiler callback. And then iCoreProfiler callback that initialize is going to be called by the runtime and with an instance of iCoreProfiler info as an argument. And then we can use that instance to interact with the profiling API. So why is it hard to write a profiler in .NET? There are multiple reasons. The first one is that there are no easy way to declare native exports in .NET. Also, we will need to consume and expose C++ virtual objects as part of the COM API. And last but not least, the profiler is loaded at an early stage in the lifetime of the process, at a time when the VM is not ready to execute .NET code. So let's go over each of those problems. So first, the fact that the profiler is loaded too early. So basically, when you start your application, you are going to launch the entry point, which will trigger the initialization of the .NET runtime. And the .NET runtime comes with its own components, such as the GC, thread pool, and type system. And during the initialization, the .NET runtime is going to load the profiler. But if we write the profiler in .NET, we will have a problem because to execute the .NET profiler is going to need the runtime, which is still initializing, and so that's not going to work. But if we switch the profiler to NativeAOT, because it's standalone, it's going to have its own runtime, which has its own GC, thread pool, and type system, and so on. And so it can rely on its own runtime and not call the runtime of the host. And so this is not a problem anymore. The next program is a native export. So let's start by explaining what it is. So I don't know if you've ever wondered how a DLL works. How is it possible to load an arbitrary file and execute functions from it? And the way it works is that the file has a header, a portable executable header, and the format of that header is well specified, and inside of it you will find the export table. And the export table contains multiple information, such as the name of the functions that are exposed by the DLL, and also their address inside of the file. And so by combining both those information, we can conclude that inside of the DLL file, we have my function at that location and do stuff at that location. And then calling a function is just a matter of mapping the DLL file in memory and then jumping to the address of the function. So of course, in practice, it's slightly more complicated, but that's the principle behind it. And so to use, one more thing. On Linux, you have the same thing. It's not specific to Windows, except that you are going to have a SO file for shared objects instead of DLL, and you're going to have an elf header instead of portable executable, but otherwise the concepts are very similar. And so to use the profiling API, we are going to need to export a function. And the problem is that this is not supported by C#, but this is actually supported at the IL level. And so there is a trick to use ILDSM to decompile your assembly, then change the IL to add your export, and then recompile it. And there is a NuGet package that does that. But that's a bit clunky, and it's not very reliable. Well, anyway, and with NativeAOT, this is supported out of the box, and you just have to add the unmanaged colors only attribute on your method, and this will generate an export. So that's one more problem taken care of. And the last problem is consuming and exposing C++ virtual objects. So what does a C++ virtual object looks like? So let's declare a simple object. So in memory, you will have the fields. And let's imagine that I declare a virtual method on that object. When that happens, the compiler is going to emit a hidden field at the beginning of the object, which is a pointer to what is named the vtable. And the vtable is a table that contains pointers to the implementation of the functions. And so if I add another function, it's going to add another entry to the vtable, which points to the implementation of that function. And so if I declare another object that inherits from the first one, it likewise is going to have a pointer to a vtable, but this vtable is going to contain different addresses because that will be the implementations of the child method. And with that, when you call a virtual method, it is compiled into an indirect call. So the address of the method is not hard-coded. And thanks to that indirection, you can have you can compile some code to expect an instance of my object, and you can give it an instance of child instead, and it will just work. And so because we need to expose an instance of iClass factory, we are going to have to create our own fake virtual C++ object. So basically, we are going to implement the iClass factory methods, so they will be located somewhere in memory. And we are going to create our own vtable, this pointer to all those functions. And then we are going to create our own fake instance that will point to the vtable. So let's get started. So I've got a solution ready. We have a test application. Inside of the test application, I just write hello world. I wait to press return, I throw an exception, and then I trigger a garbage collection. And then I have my project for the profiler. This is a classic project, except that it's compiled, it targets .NET 7, and I set publish AOT to true to use NativeAOT. And then I have a DLL main class. Here I declare my DLL get class object, and I export it. And now I need to create my instance of class factory. So we will start by declaring it in C#. So there we go. I've got all the method, and every time I just display something in the console. But I can't give this managed instance to the runtime. I need to create my fake C++ object. So for that, we need to create our vtable. So what I do is allocating some native memory, enough to store 5 pointers, because I have 5 methods. And then I need to get the address of my method to store them in the vtable. And to do that, I'm going to create some delegates. So right there, and I need to add the definition of my delegates. And so those delegates mimic the signature of those methods. And all it does is calling the method on my object. That's all it does. But because I have those delegates, now I can call marshal.getFunctionPointer for delegate. As the name indicates, it takes a delegate and it returns a function pointer. And so we can populate our vtable with those function pointers. Then we need to create our fake instance. So I allocate another chunk of native memory, this time enough to store 1 pointer. And I assign the address of the vtable to it. And then finally, I store it because we will need to use it to use the profiling API. There is one subtle error here. When you use getFunctionPointer for delegate, the lifetime of your function pointer is going to be the same as the delegate. So I need to store my delegates somewhere so that they don't get garbage collected. Otherwise, the function pointer will become invalid. And with that, I have my class factory object ready. So right there, I'm just going to add a field to store it. And now I just need to instantiate it and to return the value to the CLR. And that's it. And then once we have the class factory, the runtime is going to call create instance. And this time we need to return an instance of iCore profiler callback. But if you have a look to the interface iCore profiler callback, you will see that there are a lot, and I mean a lot, of methods. And so there is no way that I'm writing all this boilerplate code for all those methods. So instead, I prepared a source generator. And so I'm not going to explain how the source generator works because that will be another talk. But basically, you can see that it's emitting the same code that I show you. It's creating a delegate, it's adding it to the list, and then it's populating the vtable. And so thanks to that source generator, what I can do is, for instance, for class factory, I can just declare the interface with the method that I want to have and add the native object attribute. This will tell the source generator to generate all this code that I've just written in front of you. So basically, now I can just say that I want to inherit from iClass factory. I can remove this, all of this. And here, basically, I say I want to call my wrapper that was emitted dynamically. And that's about it. And it will work exactly the same way. And so now for my core profiler callback instance, I just say that I want to inherit from iCore profiler callback. And then I let ReSharper do the hard work of generating the AT methods. There we go. And then I add the code to create my wrapper. And so likewise, this is going to be generated by the source generator. And then finally, in my class factory, I need to return the instance of core profiler callback. So I add a field to store it, and then in create instance, right there, I instantiate it, and I assign it to my out parameter. Okay. Then when we return the instance of core profiler callback to the runtime, it's going to call query interface. So if you look at the documentation, you will see that there are many versions of the iCore profiler callback interface. There is 2, 3, 4, 5, all the way to 10. And so the runtime doesn't know which one we implemented. So it's going to call query interface with a GUID associated to each of those interfaces. And when we find the one that we implemented, we are going to return it to the out parameter. And so I'm going to copy paste the code. So here the idea is we check the GUID that we have as parameter. And if it's the one associated to iCore profiler callback 2, we assign our fake C++ object to the out pointer, and we return OK. Otherwise, we return an error code to say that we don't implement that interface. And then the last thing to do is the runtime is going to call initialize and give us an instance of IUnknown. And then we must call query interface on that instance of IUnknown to retrieve the implementation of iCore profiler info. And so here we have the opposite problem. Until now, we have created fake C++ objects and returned them to the runtime. And now the runtime is giving us a C++ object, and we need to call a method on it. So to do that, we are going to need a wrapper. So here is what it's going to look like. So I have the IUnknown interface. And so the idea is that I take as in the constructor the pointer to the native object and store it. I fetch the vtable with this ugly pointer logic. And then for each of the method, I look into the vtable to retrieve the address of that method. I cast it to a function pointer, and then I just invoke it. And so just like before, I don't want to write all this boilerplate code for each of my types. So I added it to my source generator. And so I have it right there. And so now in my initialize method, yeah, no, that's not the right version. So there we go. So basically, I call my native generator, which will use exactly the same code as I showed you, to retrieve my wrapper that allow me to use the IUnknown object. And I call query interface to ask for the instance of iCore profiler info 3. And then if it works, we have everything we need to actually write a fully featured profiler. So basically, we store the instance of core profiler info. Just like before, we wrap it because this is a C++ object. And then just to demonstrate that we can actually write a working profiler, I'm going to detect when the application throws an exception and dump the call stack when it happens. So here I call setEventMask to tell the CLR that I want to be notified when an exception is thrown, and that I want the capability to work the stack. And then we go to the exceptions thrown event. There we go. And I'm going to copy paste all this code. And so I'm not going to explain what it does because that's the .NET Profiler API, but I'm only using all the concepts that I've shown you before. So I'm only using my core profiler info source generator, and then it's just using the profiler API, which is quite complex. For instance, just to work the stack, there is all this code. So obviously, I can't explain to you in detail. And then we need to compile all of this. So basically, we run .NET publish to ask NativeAOT to create our native library. And I give the native lib equal shared parameter to ask to create a shared library. And so I have a bunch of warning, but we don't care about that. And to test it, I will have this command, which sets the right environment variable to tell .NET to use this profiler. And so there we go. And now if I do launch with profiler, so here we see the hello world of my console. And here we can see that there is a bunch of stuff that happened during the initialization of the profiler. So as you can see, the profiler is loaded before your application starts executing. And then if I press return, we see that we detected that an exception was thrown. We were able to tell that it's an instance of system.exception, and we were able to dump the stack. So we have everything we need to write a profiler. So the answer to can we use .NET to write a .NET profiler is yes. So moving on to the next scenarios. Now I want to know if we can use .NET to write a LLDB extension. So LLDB is a Linux debugger. And so you can write extensions to add commands to LLDB. And to do that, you need to export a plugin initialize function that will take an instance of sbdebugger as an argument. You need to call getCommandInterpreter to get an instance of the command interpreter. Then you need to implement SB command plugin interface for your command. This is a virtual interface. And finally, you need to call add command to register your command. So what is the difficulty here? We need to have native export. We know how to do that. We need to expose virtual objects. We know how to do that. And we are going to need to consume non-virtual C++ objects. So what's the difference with a virtual object? So if you remember, for our virtual object, we are going to have a vtable that is going to tell us where in memory is the implementation of the method. If you have a concrete object, in memory, you're just going to have the fields. And so my question is, how are we going to locate the implementation of the method so we can call them? And so to answer that question, we must understand how symbols binding work. So let's say that in the LLDB shared object, there is a getCommandInterpreter function that is declared. So if I write my plugin in C++, I'm going to include the debugger header, and then I'm going to call getCommandInterpreter. And so my question is, by what magic this call is going to find the implementation of getCommandInterpreter? So when explained like that, it may not be obvious what the difficulty is. So let me rephrase a bit. On one side, we have the LLDB shared object, and somewhere in that file, we have the getCommandInterpreter function anywhere. And then at runtime, we launch LLDB, and the shared object is going to be loaded somewhere in the process at a random address. And then on my side, I write a plugin, and I call getCommandInterpreter. So this is going to be compiled to a call instruction at the assembly level with an address. And my question is, by what magic does this address that is defined at compilation time going to match this address that is only known at runtime? Well, if you remember, I explained that we have an export table on the shared object. And it turns out that we also have an import table. And the import table is going to say that we want to use getCommandInterpreter, and it's going to associate a fake address to it. Then when we compile our code and we call getCommandInterpreter, this is going to be compiled to a call instruction, but it's going to call the address that is stored in the import table. So it's an indirect call. It's going to fetch the address from the import table, and then it's going to call it. How does that help us? Well, there is one component that is going to make everything work, and this is the loader. So I've put it on the side, but it's actually inside of the process. And the idea that at runtime, we are going to load LLDB.so, and the loader is going, let's say that we load it at address 1000. The loader is going to have a look at the export table, and here it's going to see that there is a getCommandInterpreter function at offset 50. So the loader is going to think, okay, LLDB was loaded at address 1000. Then getCommandInterpreter is exported at address 50. And so if we add them, I know that in my process, I have get command interpreter at address 1050. Then we are going to load the plugin. The loader is going to check the import table, and inside we say we want to be able to call get command interpreter. And so the loader is going to say, hey, I know where this method is. It's at address 1050, so it's going to patch in memory the import table with the right address. And since our call was compiled to an indirect call to the import table, we will end up invoking the right function. So it means that all the magic is happening in the import table. So all we have to do is to declare an import and call it. We know how to declare an export, but unfortunately, we have no way, at least no way that I know, to declare an import in a .NET application. So we will have to find another way. The first workaround is to add a C++ wrapper to expose the LLDB object into virtual function, because we know how to consume virtual function. So the idea is that we have the get command interpreter function as a concrete function, and the wrapper creates a class that wraps the SB debugger and expose get command interpreter as a virtual function. So I tested it, that works properly, but that means that we will have to write some C++, and we are trying to avoid that. So solution number 2 is somehow to dynamically locate the functions at runtime. How can we do that? Well, we know that the loader knows where the function is, and it turns out that there is a way to ask it where it is. So on Linux, we do that with dlsim, and on Windows, we do that with getProcAddress. So all we have to do is to call the function to get the address of getCommandInterpreter. So going back to Visual Studio, I have my project for LLDB. And so I export a plugin initialize function. Here you can see that it's exported with a weird name. I will explain why later. And it takes a pointer to an instance of SB debugger, and we call get command interpreter on it. And inside of it, the idea that we call native library.getExport. So that's a .NET API that maps on dlsim on Linux or getProcAddress on Windows. And we say we want the address of get command interpreter. Then once we have the address, we cast it to a function pointer, and we invoke it. And so this is going to return an instance of SB command interpreter. And here you can see that I declare it as a struct. That because in the profiler API, everything was references, but in the LLDB API, they are passing all the objects by value. And so I have to use structs to have the same copy semantics. And since this SB command interpreter object on the C++ side has one pointer in size, I add one pointer field here to have the same size. But if I do that, this is not going to work. This is not going to work because of something called mangling. So what is mangling? For historic reasons, C++ functions are exported with names compatible with C. So from what I've read, that's because in the early version, C++ was compiled into C code and then fed to the C compiler. So all the C++ concepts had to be translated into C. But the problem is that many of those concepts don't exist in C, such as namespaces and templates. And so to convert C++ in C, we have somehow to convert those names into names that are accepted by C. And this is what we call mangling. And so, for instance, the get command interpreter at compilation time is changed into this thing. So that means that here in my code, instead of calling the full name of the function, I will have to call this. But my issue is that at some point, because there are a lot of functions in the LLDB API, I want to be able to write a source generator, just like before, that will emit this boilerplate code. But for that, I will need to dynamically generate this name somehow. And it's technically possible to write a mangler in C# because the specification is public. But the problem is that the mangler signature is going to vary depending on concepts that do not exist in C#. For instance, the const keyword is going to change the mangler signature, but const has a very different meaning in C# and in C++. And so that means that when declaring my interface that I will give to my source generator, I need to add attributes to declare all those concepts that don't exist in C#. And so at the end, this is going to be clunky. And at this point, I may as well just add the Mongo name in an attribute. But that means that I will have to find the Mongo name for each and every function in the interface. And I'm way too lazy to do that. So we need another solution. So we know that the loader don't actually have the address of getCommandInterpreter, but the address of the Mongo name. Okay, and I'm supposed to call DLSim with the Mongo name to fetch it. But what if there was a way to get all the symbols known by the loader, and then we can do some kind of fuzzy matching to find the one that has getCommandInterpreter in it. If I use a string that is precise enough, then my fuzzy matching algorithm might be enough to for the purpose. But unfortunately, there is no API to get all the symbols exported by the loader. So instead, what we can do is locate the module in memory and do what the loader would do, which is pass the elf header and extract the symbols from the export table. And so that's what I did. Well, I say I, but it just code that I shamelessly copy-pasted from Stack Overflow and then converted from C++ to C#. So I'm not going to explain it, but basically it locates the module in memory and then it parses the export table to find all the symbols. And then I have a find method that is going to take the name of the method and is going to do some fuzzy matching to find the symbol that best match the method. So thanks to that, instead of writing the Mongo name, I can just write method locator.find and find the method. So now we can test if it works. So I'm going to publish my project. And then to test it, I'm going to launch LLDB and tell it to execute plugin load my plugin at startup. So native compilation takes a bit of time. There we go. And if I test it, we can see that we crash with a segmentation fault. And the problem is the ABI. So what are we talking about? So you already know that the CPU has registers. And when we have a function and that we're going to call it, we need to store the argument, the value of the argument, in some registers. And what registers to use is defined by the API for application binary interface. And on Linux, is going to use the systemv API. And so what does it tell us? So in this case, we call do something and we give it 2 pointer size arguments, and it's going to return a pointer size argument. And so here we're going to store 1 in RDI, 2 in RSI, and when returning, the function is going to store 3 in RAX. So far, so good. So now let's say that we're going to return a payload that has 2 pointers inside. So just like before, we store 1 in RDI and 2 in RSI. And then since it's not going to fit in a single register, the method is going to store 3 in RAX and 4 in RDX because there are 2 registers dedicated to return value. So let's say that our struct has 3 or more pointers. So when we call the method, something different is going to happen this time. In RDI, we're not going to store 1, but a pointer to an area in memory. Then in RSI, we are going to store 1, and in RDX, we are going to store 2. And then the function is going to copy the struct to the address that was stored in RDI and return that address in RAX. So thanks to that, the caller can basically allocate enough memory for the struct, usually on the stack. Then it gives a pointer to that location to the method, and the method can copy any struct of any arbitrary size to that memory location and returns it. And that's how we can return any struct from the method. But in our case, SB command interpreter just contains one pointer, so it fits nicely in a single register. So how does that impact us? And oh yeah, this way of returning a struct is named a return buffer. And the problem is in the specification of the system VABI, and it says that a struct class or union object can be returned from a function in registers only if it is sufficiently small, that's the case, and not too complex. And if the object is too complex or doesn't fit into the appropriate registers, then the caller must supply storage space, yada, yada, yada. So basically, if it's too complex or doesn't fit in the register, then we use a return buffer. And the problem is that if we check the implementation of SB command interpreter in the LLDB API, it declares a destructor. And the system VABI says that if an object declares a constructor, then destructor is considered as complex, and therefore it must be returned on a return buffer. And here we have a big problem because here C# or .NET has no way to know that we are actually storing a complex C++ object. Here, C# or C a simple struct, and so it thinks that it can use a register. So how can we force C# to return this object in a return buffer? And so I checked the source code of the CLR, and I found this function, classify 8 bytes with NativeAOT. And the command says returns true if the struct is passed in registers or false otherwise. So basically, this is the function that will try to find out if a struct can be returned in the register. And if not, it's going to use a return buffer instead. And if we check the code, we see that first it checks if the struct has an explicit layout. So if it has a struct layout attribute. If it doesn't have a layout, then it's going to use another logic. But if we specify the layout, then it's going to check if there are fields, and if not, it's going to return false. So I really don't know why there is this rule, but this is great for us because it means that all we have to do here is to switch to an explicit layout and remove the field. And in theory, the runtime should use a return buffer instead of a register. So I need to publish my project again. Short pause. NativeAOT compilation takes more time than managed, unfortunately. There we go. And if I launch LLDB, then we don't crash. And now we have everything we need to write our plugin. So just like before, I wrote a source generator to generate this boilerplate code. And so I'm just replacing the object to use it. There we go. And so now we can finish writing the plugin. I need to copy paste this. There we go. And so what we do, we call get command interpreter, we get our interpreter. Then we need to implement SB command plugin interface for our command. This is a virtual interface. So I'm using the same source generator as the profiler. And so my implementation of my command, I just display OK, that's it. And then I add my command with this name and this description. And so if we compile just one last time. And so yeah, C#11. And we try in LLDB. So if I run help, here we can see my command with the help text. And if I run it, then it's going to display OK. So this is working. And so can we use .NET to write an LLDB extension? The answer is kind of. Technically, it works. But I wouldn't recommend you to do that because the fuzzy matching to find the Mongol name can be unreliable, say if you have an overload of a function. And so you're probably better off writing a wrapper in C++. But technically, it works. And so moving on to the last scenario, and because this is the Dotnetos Conference, we're going to check if we can use .NET to write a .NET garbage collector. And so that will mean that our garbage collector will have its own garbage collector because it will have its own .NET runtime. So this is perfectly useless, but fun enough to try. So if we have a look at the GC API, it's deceptively simple. Basically, we need to export a GC version info function, and we need to export a GC initialize function, which is going to return an instance of IGC heap and IGC handle manager, which are all virtual interfaces. And we use IGC to CLR to interact with the CLR, and likewise, it is a virtual object. So what is the difficulty? We need to declare native export. We know how to do that. We need to consume and expose virtual object. We know how to do that. And we have the same problem as the profiler, which is that the GC is loaded very early in the process at a time where .NET cannot execute the IL yet. But we've seen with the profiler that this is not a problem when we use NativeAOT. So I guess that could work. So I have my garbage collector project right there. And so in the DL main, I export a GC initialize function. And so I'm not going to detail the code, but I use exactly the same source generator as before. I wrap the CLR to GC virtual object, and I have wrapper to return my own object. And in GC version info, you need to return what version of the GC API you support. All right. And then to test it, I have this file where we set this environment variable, which is going to tell .NET to use this garbage collector. And so I've already compiled it before. I already compiled it before. And if I launch it, we can see that we crash with an access violation. So what is going on? So this one was very unexpected. And the idea is that when we start the application, we execute the entry point. This is going to trigger the initialization of the runtime. And the runtime is going to load our custom garbage collector, which exposes GC underscore initialize. And so the runtime is going to call GC underscore initialize. So far, so good. To execute GC underscore initialize, since we are inside of NativeAOT, it's going to initialize its own runtime. And since we have, well, the NativeAOT runtime has its own GC, it has its own GC underscore initialize function. And so we expect that it is going to call it to initialize its own GC. But for some reason, this is not what's happening. And instead, it's calling back our own GC underscore initialize, which causes the crash. And I'm not 100% sure of why this is happening, but part of the answer is that if we check the NativeAOT runtime, the source code of the NativeAOT runtime, we can see that the GC underscore initialize is written as an export. And the problem is that in an application, you can have only one export with a given name. And so it looks like the GC underscore initialize of the runtime is overridden by the GC underscore initialize of our garbage collector. And I couldn't find a way around that because even if you write a simple NativeAOT console application, so you're not even trying to write a garbage collector, and you expose a GC underscore initialize function, then your app will crash at startup. So in NativeAOT, you simply cannot export GC underscore initialize. So I couldn't stop there. So what I did is basically I renamed GC underscore initialize to custom GC underscore initialize. And then I added a loader written in C++ that exports a GC underscore initialize. And the idea is that I register the loader as a garbage collector. So the .NET runtime is going to call it. And then the loader calls custom GC underscore initialize in my garbage collector. And so then it can properly initialize the runtime because I'm not overriding the GC underscore initialize function. And so that's what I did. I have my loader right there. I'm not going to detail it, but basically I load garbage collector.dll and I call custom GC and custom GC. And so here I need to rename them to, no, sorry, here to custom. Okay. Then I need to publish it. And so I didn't write a fully featured garbage collector because I simply don't have, oh yeah, sorry, there is this bug. Because I simply don't have the time. And so what I did is I took the bump pointer GC that was written by Conrad. So basically what it does is it just allocates memory and never frees it. And also as a bonus, when there is a garbage collection, I dump all the content of the heap to the console just to show that we can work the heap. And so with that, I launch my app with a loader. So launch GC with loader is going to use the loader as a GC instead of my NativeAOT file. And so here we see that we arrive to hello world. We see that the GC was properly initialized. And then if I press return to force a garbage collection, we see that it's able to dump all the content of the heap. So can we use .NET to write a .NET garbage collector? The answer is unfortunately no. You will have to, you can write most of the logic in .NET, but you will need this little wrapper in C++ to bootstrap it. So that's it. You can find the source code of this presentation in the Dotnetos 2022 repository. And then I have a dedicated repository for the managed profiler and the managed GC, because that's a project that I plan to work on in the future. And yeah, don't hesitate to check my blog and ping me on Twitter if you have any question. That's it.
Okay, we need to calm down a little because we saw so, awesome amount of knowledge and techniques that we need to rest a little. Awesome talk. We have some questions, and as the time is running slowly, I will just give a chance to answer at least some of them. So I have one question from Discord that I will display, and it was where? Here. Do you see the question on the?
How does NativeAOT never change the ability to interop with other language, C or Odin, for instance? Okay. So the idea is that because thanks to NativeAOT, you are produce a native library. It means that you can technically extend any application that support native extension. So if you have an application that you could extend with C or Go or Rust or you name it, then now you could use NativeAOT for it.
Awesome. Another question is ready to run available for WPF or Windows Forms?
So personally, I've never used Ready to Run, but as far as I know, it should work for any kind of application. There's no reason why it would be limited to console application.
The same question for NativeAOT.
Same answer.
Awesome. That was quite fast. Is your code available on GitHub? You have you see it on the slide.
That's what
for sure I will look. I also allowed myself to give some sneak peeks on Twitter already, so there are some discussions.
Yeah.
You can look later. And the very last question.
Interesting using a custom GC for specific. Oh boy, I prefer scenario. I've debated moving to another language, but that's more a question for you, Conrad. But
yes, we can write it. No one has did it besides this super trivial case that it just provides the proof that it is possible. So we need to wait, or maybe you can write your own if you need. Like the whole infrastructure is theoretically there, but still it is missing these APIs that are there. So we are in the middle ground, I believe, here. I would, as a kind of an answer, it is possible, but I would not rely on it. And probably if you need something super specific, just look whether the current or next versions of GC are giving you something more. But I would not rely on waiting that someone will write it in some newest feature.
Also, I would add that there are some limitation in the .NET API, and so if we had the time to write a custom garbage collector, personally, I would probably fork the runtime and directly modify the built-in GC rather than using the API.
Exactly. Which is even more, I mean, at least doable, but not trivial thing.
Yeah.
Okay. Thank you very much for this awesome talk. I hope people are just having time now to rest a little before the next one. It was super interesting. You have some questions on Twitter also, as I saw, so you can come back to them. And thank you for being with us. See you somewhere in Prague, as far as I know.
Yeah, thank you. See you.
Thank you. Bye. And we will see in a few minutes on the very last session today. So stay with us. Thank you.
All right.